All right, good afternoon and welcome to Master Talker online class. In today's video, we'll be talking about electric potential, right? Electric potential at any point in an electric field is the work done in bringing a unit positive charge from infinity, okay, to that point against the electric force of the field. All right. The electric potential V is positive when the work is done against the field. If the work is done against the field, then it is positive. They will ask you that if electric potential is positive, what does it mean? It means that the work done is against the field. But if it is negative, then the work is done by the field itself. Okay. If it is positive, if you have a positive answer for electric potential, it means that what? That the work is done against the field. Okay. But if it is negative, then the work is done by the field itself. Please, you need to know that. Very important. All right. Then note that the positive potential is taken to be higher than the negative. Okay. This is why in an electric cell that the positive terminal is at the higher potential than the negative terminal. All right. So let us consider 2 points. Consider 2 points in an electric field as shown below. We have this. We have positive inside here. Then we have a point A and point B. Okay. We now have, this is how the charge is moving. All right. So I now have that okay. All right. The electric potential V at point A is higher than the electric potential at point B, since more work is done in bringing a unit positive charge from infinity to point A than to point B. All right. Thus, there is a potential difference between point A and B. The potential difference is the exact work done in bringing the charge from point B to point A. All right. So you now write potential difference. Potential difference. Okay. All right. The potential difference between 2 points in an electric field is the work done in moving a unit positive charge from one point to the another. So the work done in moving a unit positive charge from here to here is what is called a potential difference. Okay. Is what is called a potential difference. So you write for me. Potential difference is what? Work done per unit charge. Okay. Potential difference is work done per unit charge. That's another way to define potential difference. Potential difference is work done per unit charge, so measured in joule per coulomb. Okay, because work done is measured in joule, and then charge is measured in coulomb. So don't forget, potential difference is presented with V. V is equal to what? Work done, and work done is force times distance. Don't forget that work done is force times distance divided by what? By the charge. But don't forget that the formula for your force is equal to what? KQ squared, okay, over what? R squared. That is your force. So if you put it here, if you put it for potential difference, you now have that potential difference is equal to, instead of putting force here, I'll put what? KQ squared all over what? R squared times, what is left is now is S over R over Q. And S is distance and R is equally distance. So let me change this S from S to R as distance. So I'll have what? R over R squared. So if you look at this, sorry, R over Q. What am I saying? R over Q. So if you look at this now, one of these is taking care of one of these, because there are two here. One of these is taking care of one of these. So I am left with what? KQ over R. That is my what? My potential difference. And don't forget what is the value of your Q. Your Q is 1 over 4 pi E naught. So my potential difference is equally what? Q all over what? 4 pi E naught. Then you put your R. So that is another powerful formula for potential difference. All right. So let's solve some calculations to illustrate what we have just said now. So the first thing we're going to solve said calculate example. They say calculate the potential at a point 30 cm from a charge of 1.5 times 10 raised to power minus 5 coulomb. Solution. Very, very simple. What do we do? They've given us the distance r. My r is 30 cm. Convert it to meter. I have what? 30 divided by 100, which is what? 0.3 meters. Okay? The next thing they gave us is the charge. 1.5 times 10 raised to power what? Minus 5 coulomb. I know that my potential difference is what? KQ over what? R. Don't forget that here is supposed to be squared, but in potential difference, there is no square. If it is force, it will not be squared. So don't forget that your K is always a constant, 9 and 9, which is what? 9.0 times 10 raised to power what? 9. So you have what? If you put it 9.0 times 10 raised to power 9 times my Q is what? 1.5 times 10 raised to power minus 5. All right. Then divided by your R. What is your R? 0.3. So if you now do that, you'll be having divide with your calculator, you have 4.5 times 10 raised to power 5 in what? In potential work done per unit charge. So work done is joule per coulomb. So work done per unit charge. So that is that. Very, very simple. So let's take the next question on this. Question number 2. Question number 2 said a point charge of magnitude 2.5 μ coulomb is moved through a distance of 0.04 meters against a uniform electric field of intensity 15 volts per meter. All right. Then I say calculate the work done. Calculate the work done by the charge. Okay. Solution. Now they gave me the first thing they gave me here is the charge. They gave me the charge as 2.5 μ coulomb, which is what? 2.5 times 10 raised to power minus 6 coulomb. Okay. The next thing they gave me is the distance. The distance is 0.04 meters. What else? They gave me electric field strength. Electric field strength is what? 15 volts per meter. All right. But I know that electric field strength is equal to force over what? Force over charge. Don't forget. So for me to get my force, I'll be having that force is equal to what? The charge times what? Times my E. So if I have that, I'm going to have 2.5 times 10 raised to power minus 6 times what? 15. So if you do that, you're going to have multiply by 15. You will have do that. You get your answer. So whatever you get here, so because I don't have my calculator here, so do that to get your F. But don't forget that what? That your potential difference is what? KQ over what? In fact, force work done per unit charge. Thank you very much. That my V is equal to what? Work done per unit charge. And what is work done? Force times distance is equal to work done. Is it not true? Then divided by my charge. What is my force? My force is all these things. So my force is what? 2.5 times 10 raised to power minus 6 times that 15. Because I did not get the answer. So let me use this thing here. This is my force. Then my distance they gave me is what? Times 0.04. That is the distance they gave me. Now divided by what? The charge. The charge there is what? 2.5 times 10 raised to power minus 6. So if you do everything there, you'll be having what do I have? So if you do everything there, you'll be having 4.5 times 10 raised to power 5. Sorry. So that's the mistake. So they say I should calculate the potential difference. Oh, they say I should calculate the work done. So the work done is only the one at the top, please. They say we should calculate only the work done. So we are calculating work done only. So work done. So we are calculating the work done. So the work done is equal to multiplying this. And if you multiply that, you'll be having that your work done is equal to 1.5 times 10 raised to power minus 6 joule. Okay? That is my work done. But if they say I should calculate my potential difference, it's not different. It's not difficult, sorry. Work done per unit charge. That is my potential difference. But they are not asking me that anyways. So the next thing, question number 3. And question number 3 said, an isolated electrically charged sphere of radius r and the charge q is supported on an insulator in air of permittivity E0. Then I say write down I an expression for the electric field intensity on the surface of the sphere. Okay, I an expression for electric potential at the surface of the sphere. I a relationship between the electric field strength and the electric potential at the surface of the sphere. Right? Okay? So, what are we asked to do here? Okay? Oh, the question is not yet done. So, let's continue the question. The question is not yet done. Then the next question there, they said, okay, that is number, they said the C question, that is IV. They said the plates are parallel. The plates are parallel plate capacitor, comma, 5.0 times 10 raised to power 3 minus 3 apart. Okay. Are maintained at 5.0 times 10 raised to power 4 volts. Calculate the magnitude of the I electric field intensity II, the force on the electron, III, acceleration on the electron. Okay, so let's start from here. The first question solution. So this is question number 2. This is question number 1. All right. From question number 1I, said that we should get the expression for the what? For the electric field intensity. And I know my formula. Just write the formula. Electric field intensity, according to what they gave us, is what? Don't forget that it's supposed to be KQ squared over what? KQ over what? Over R squared. But they did not tell us Q, since they gave us permittivity. So I'm going to have my K is set as what? Q over what? 4 pi E naught. All right? 4 pi E naught R squared. So that is the formula you are required to get. As simple as that. Very, very simple. So number 2, this is 1II. 1II said we should get an expression for the potential difference. Potential difference V is equal to what? KQ over R, which is what? Q over what? 4 pi E naught, then R. Very simple. So what do you have now? III said the relationship between the electric field strength and the electric field potential. Okay? So the relationship is simply if you look at this now, if you remove if you put do you know that this thing is the same thing as saying Q over 4 pi E naught R times 1 over R again? Is it not true? Because R times R will give you this R squared. But I know this man is the same thing as what? As your V. So which means my E is set as what? V over what? Over R. Okay? So you say that V is equal to what? R E. So anyone that you write is very, very correct. Very, very correct. Okay? So that is what we are required to do. So now let us solve the question given to us. That is question number 2 there. So for question, we are done with question number 1. For 2I said we should calculate what? Calculate the electric field strength. Okay? And I know that electric field strength E is equal to what? Charge per coulomb. Sorry, Newton per coulomb. That is force per unit charge. Force per unit charge. All right? So do we have the force or do we have the charge? So what did they give us? Oh, volt per meter. Volt per meter. Don't forget that electric field strength is equally volt per meter. So they gave us the potential difference. Potential difference all over what? The distance. So which is what? The volt there is what? 5.0 times 10 raised power 4 divided by what? The distance there is 5.0 times 10 raised power what? Minus 3. So I'm going to have 1.0 times 10 raised power 7 in what? In volt per meter. Okay? In volt per meter. Very, very simple. So the next thing they say we should calculate is what? Calculate the force on the electron. But I know that my E again is what? Force per unit charge. Okay? So my force will now be what? Charge times my E. So and what is the charge there? Do we have the charge? Okay, the charge of electron. Don't forget that charge of electron is 1.6 times 10 raised power what? I think minus 19. I used to forget it. Minus 19, very correct. Then times the E. I've gotten my E as 1.0 times 10 raised power what? 7. So what do we have? 1 times this will give you 1.6 times 10 raised power. Remove 7 from here, have minus 12. Okay? So that is that. So the next thing they say we should calculate is the acceleration. This is my II. So for my III, I know that what? Force is equal to MA. Okay? So therefore my A is what? The force over M, which is what? The force I have 1.6 times 10 raised to power minus 12 divided by my M is mass of electron. And mass of electron is 9.1 times 10 raised to power minus 31. So if you do that, you're going to have 1.76 times 10 raised to power 18 meter per second square. So that is that. It's a very simple question to calculate. All right. So we move to the next question. The next question here said, for two charges Q1, which is equal to 4.0 times 10 raised power minus 4 coulomb, okay, located at point A, and another charge Q2, which is equal to 3.4 times 10 raised power minus 2 coulomb, located at point B, where the distance AB is equal to 0.34 millimeter. Okay, they say calculate I, the electric field strength. Calculate the electric field strength. Okay, electric field strength E. Electric field strength E at A and B. Okay, full stop. They say give okay, sorry. Then I, they say we should calculate the potential energy. Calculate the potential energy of configuration on charge Q1 and Q2. All right. So solution. So we will have that what? That E, the electric field strength is equal to what? Don't forget KQ over what? R squared. All right. We will say Q1. So, but since they are two, you say plus another one again, KQ2 over what? R squared. All right. Since they are two. So what do you do now? Now your K and R are the same thing. So I'll have the what? K over R squared in bracket of what? Q1 plus Q2. Okay. In bracket of Q1 plus what? Q2. Okay. Because K is a constant. So what do I have? 9.0 times 10 raised to power what? 9.0 times 10 raised to power 9 divided by the distance apart there is what? 0. My R is equal to 0.34 millimeter. So if you change it, it's going to be what? 0.34 divided by 1000. So what do you have? You're going to have 3.4 times 10 raised to power minus 4. All right. So you have it 3.4 times 10 raised to power minus 4 all squared. Then times my Q1 is 4.0 times 10 raised to power minus 4 plus 3.4 times 10 raised to power what? Minus 2. So if you do that, you are going to have that. Now, if this times 10 raised to power something will confuse you, convert it first. This is moving 4 times. If I move 4 times, I'm going to have, okay, this is 9.0 times 10 raised to power 9 divided by 3.4 times 10 raised to power minus 4 all squared into, if you convert this one means 0.1234. All right, plus convert this one, it means 0.03412. So if you add both of them, then you do everything now. If you do everything, you're going to have You're going to have 3.11 times 10 raised to power 13 volt per meter or Newton per coulomb, anyone you like. Okay, so number 2, II. The II said we should calculate the potential energy. Okay, the potential energy, that is the work done. If you know, energy and work done is the same thing. And what is work done? Work done is what? Force times distance. So we have the potential energy as the work done. The work done, which is what? The force times distance. All right, the force times distance. And what is your force? Don't forget that my force is what? My force is what? KQ1 Q2 all over R squared. All right, times the same R again, the distance. So if one of these R cancel one of this R, I'm going to have KQ1 Q2 all over what? R. So which is what? What is my K? 9.0 times 10 raised to power 9 times my Q1 is 4.0 times 10 raised to power minus 4 times my Q2 3.4 times 10 raised to power minus 2, then divided by my R. My R is 3.4 again times 10 raised to power minus 4. So if you do everything there, you'll be having 3.6 times 10 raised to power 8 joules. So that is my potential energy. Don't forget that energy and work done is the same thing. So this thing is what? Your potential energy. Energy and work done are the same. So that is that. All right. So we move to the next question. The next question here said a charged oil, a charged oil drop of radius 0.00013 cm is prevented from falling under gravity. Is prevented from falling under gravity by the vertical field between two horizontal plates charged. Okay, charged to a potential difference of 8340 volts. 8340 volts. Okay, then I say the distance between the plates is 1.6 cm, and the density of oil is 920 kilogram per meter cube. Okay, then I say A, calculate the electrostatic field strength. Calculate the electrostatic field strength between the charges. Calculate between the charged parallel plates. B, calculate the mass of the oil spill. The mass of the oil drop. C, calculate the magnitude of the charge of the oil. Calculate the magnitude of the charge of the charge on the oil drop. Okay, solution. Bring out your parameter solution. Now the first thing they gave us is the distance. Okay, they said that what? They gave us radius. Okay, they gave us that the distance is what? The distance between them. Okay, they gave us radius. Let's say that this is radius. Radius r. I wrote radius here so that you will not differentiate, you will not take this r as the distance apart. So the radius they gave me is what? 0.00013 cm, which is what? 0.00013 divided by 100, which is what? 0.1231213, which is what? 1.3 times 10 raised to power. How many are they? 1, 2, 3, 4, 5, 6. 10 raised to power 6 meters. All right. So the next thing they gave me is they gave me the volts. The volts as what? Potential difference. That is 8340 volts. Okay. And they gave me distance. The distance they gave me is what? 1.6 cm, which is what? 1.6 divided by 100, which is what? 0.016. Is this still not too much? 1, 2. Okay. Yeah. So what do we have now? They say we should calculate the electric field strength. Electric field strength is set as what? Volts per meter. So that is potential difference over distance, which is what? 8340 divided by 0.016. So if you divide that, you're going to get 5121250 in volts per meter. Okay, that is the first thing. Now the second thing they say we should calculate, sorry, this is A. The second thing they say we should calculate is calculate the mass on the oil, the mass. Okay, if you are calculating the mass, you should not forget that that density is mass over volume. Density is what? Mass over volume. And they are talking about so the volume we are going to use here, let's get the volume. The volume we are going to use is 4/3. That is volume of a sphere. 4/3 pi r squared. Right? 4/3 pi r squared. That is what? 4/3 times 22/7 times my r there is what? 1.3 times 10 raised to power 6 all squared. So to calculate the mass now is what? V times your density. So what is my V? 4/3 times 22/7 times 1.3 times 10 raised to power 6 all squared. So sorry 3, not squared. This is 3 because it's volume. 3. So all raised to power 3. This is my volume times my rho. My rho is the density. The density they gave me is 920. So times 920. So if you do everything here, you'll be getting 8.47 times 10 raised to power what? Minus 15 kg. So that is my mass. Okay. So the next thing they say we should calculate is the charge. The charge. Let me clean here. Okay. For C, for you to get the charge, I should always remember that what? That my E is what? Force per unit charge. Force over charge. Okay. So the charge, therefore, the charge should be what? EF over E. Over E. So what is my F? Don't forget that F is mg. Mass times acceleration due to gravity. So which is what? Mg all over what? All over your E. So put your M. You have gotten your M. Then times 10. So permit me to finish it here. So my charge will now be what? Mg over what? Over my E. Which is what? My M is what? Is 4. Sorry. My M is 8.47 times 10 raised to power minus 15 times 10 acceleration due to gravity, then divided by my E. I've gotten my E there as 5,21250. So divide everything, you get your last answer. Right? We move to the next question, and which is going to be the last question we're going to solve for potential difference. right? So the next question here said, how many electrons would how many electron would have to be removed from a metal coin to leave it with a charge of 4.2 times 10 raised power minus 6 coulomb. That's the first question. Question number A. Question number B said, if two of such coins are placed are placed are placed are placed 1 meter apart, okay, in liquid of relative permittivity 2.5, okay. Then I say calculate the force between the coins. C, what work will be done in bringing the coin 0.3 meter closer, okay. So this is very, very simple solution. So what do we do now? The first thing they say we should do, the A question here said we should calculate the what? They say how many electron will be removed. Now, how do you do that? How many electron will be removed? I think the number of electron, how many electron? So the number of electron to be removed, okay? How many electron would have been removed from a metal or to leave this? Okay, so the number of electron is simply the charge of the coin, or total charge of the coin, then divided by the charge of electron. Okay, so don't forget that charge of the coin divided by the charge of the electron, which is what? 4.2 times 10 raised power minus 6 divided by charge of electron is always 1.6 times 10 raised power minus 19. Okay, so if you do that, you're going to have 2.63 times 10 raised power 13. No SI unit because coulomb will cancel coulomb. That is that. Question number 2. The question number 2 said, if two of such charges are placed 1 meter apart. They've given me my radius as what? 1 meter. Okay, 1 meter apart in a liquid of relative permittivity. They gave me ER as what? 2.5. Okay, they say calculate the force. Don't forget that your force is equal to what? K Q1 Q2 all over what? R squared. All right. But if there is a relative permittivity, you must add that relative permittivity here. So it will not be relative permittivity times R squared. But they say that the charges are the same. So I'm going to have that it's supposed to be KQ squared all over what? Relative permittivity R squared. So what do I have? My K is always 9.0 times 10 raised to power 9 is my K times the charge there. What is the charge? The charge of the coin, that is 4.2 times 10 raised to power minus 6 all squared. Now divided by my permittivity is 2.5 times my R squared is 1 meter squared, that is 1 squared. So if you punch everything in your calculator, you will be getting you'll be getting 0.064 Newton. All right. So that is that. So let us answer question number 3. Question number 3 said, what will be the work done in bringing the coin 0.3 meter closer? If you are bringing it 0.3 meter closer, it's simply that the work done should not be what? The work done when it is in 1 meter. The work done when it is in 1 meter, 1 meter, okay, minus the work done when it is if you bring it closer, if you remove 1 from that 0.3, it will remain 0.7. So it is at this 0.7 now. So work done when it was complete, then minus work done when it is at 0.7. Okay, so that is how to calculate that. Let me check if I'm correct. Yes, I'm very, very correct. So what do we have now? We're going to have, don't forget that work done is force per unit charge, and the work done is always KQ over what? Over R. Don't forget that there is no what is it called? There is no squared in work done. But don't forget your permittivity. So you must put the ER under. Okay, so minus the same thing again. KQ over what? ER, then R. Okay, and this, don't forget that this R is for when it's 1 meter, and this R is for 0.7 meter. So if you see that all of these things are the same thing apart from the R here, so I'll have that my K all over what? ER KQ over ER in bracket of 1 over R minus 1 over R. And this R is for the 1 meter, and this R is for 0.7 meter. Okay, you can call it R1 and R2 anyways. So calculating that, you'll be having that we are bringing it 1 meter, we are bringing it closer. So that is how to solve when you are bringing it closer. So I'm going to have that my K is 9.0 times 10 raised to power 9 times my Q is the charge of the coin, which is 4.2 times 10 raised to power minus 6, all right, divided by my ER is permittivity, which is 2.5, then into 1 over 1 meter, 1 over 1 minus 1 over 0.7. All right, so you're going to have that you're going to have 9.0 times 10 raised to power 9 times 4.2 times 10 raised to power minus 6 divided by 2.5 into the LCM here is 0.7. So 0.7 divided by this is 0.7. 0.7 times this is 0.7. All right, minus 0.7 divided by this is 1. 1 times 1 is 1. So I'm going to have okay, sorry, it should be at 0.7 minus at 1. Yes, sorry, it should be at 0.7 first before 1, at 0.7, because we are not supposed to get negative and at 1 meter. Okay, sorry about that. So this one is for 1 meter, while this one is for 0.7. So I just noticed it because I'm getting negative. So this is 0.7 and then at 1. So this is 0.7, then this is 1 and then 0.7. So I'm going to have 9.0 times 10 raised to power 9 times 4.2 times 10 raised to power minus 6 times, if you do here, you're going to have, sorry, this is divided by 2.7, while this is divided by 0.3 over 0.7. So if you calculate everything, you're going to have 0.03 joules. So thank you very much for watching. In our next video, we'll solve more calculation on everything we have done in video 1, 2, 3. Okay, more examples. Then we'll now enter the next topic. Thank you very much. God bless you. Don't forget to like, share, and subscribe.